Hey everyone, welcome to Chemistry 1111. Dr. Carroll here. Today, the first lecture of Unit 5, where we're going to learn all about electron configurations and periodic trends on page 209, Unit 5. So, recall we looked at orbitals near the end of last class. So we have that. Then I see a firework here. You can see an excellent podcast about fireworks by yours truly on All This Science. All This Science, available on iTunes and many other places. So we're going to look at orbital energies, the structures of the periodic table, the greatest invention of all time. In 2012, I convinced 30 million Canadians on national television that it was. I can show you that clip one day. Electron configurations, periodicity of atomic properties, energetics of ionic compounds, ions, and chemical periodicity. So all that stuff we're going to look at here. We're going to start with orbital energies, and we will talk about the fact that orbital energies vary with nuclear charges, and that's going to help us with our periodic trends and just understanding everything and filling up electrons. Here we have ground states and things like that. Nuclear charge, you'd think if you had no electrons intervening between a nucleus and a valence electrons of course meaning the outermost electrons, that the valence electrons would feel the full force of those protons in the nucleus. But there are intervening electrons, intervening orbitals. Some intervene more than others, and this has an effect on the periodic properties like first ionization energies, electron affinities, electronegativities, atomic radii. Again, things that you should remember a little bit from last course, but if not, well, we're going to go over some of it here. I see here that I haven't chosen a pen. What color shall we choose today? Should we change it up? Oh, let's use this nice blue color. Oh, that's good. Speaking of colors, look here. We have some review here on emission spectra. Helium plus, which just has one electron. It's a little bit different than the hydrogen. The emitted photons have different wavelengths and energies because the helium plus has quantized energy levels that are different from hydrogen, right? Helium plus is going to be slightly different than hydrogen because it's got two protons and one electron as opposed to one proton and one electron. Helium plus binds the electron with a stronger force. See that? Helium plus N equals 1, way down at minus 50, 200, something like that. And then there's hydrogen around minus 13, 12, I think. So bottom line is helium plus is more stable than is hydrogen. Okay, so that's useful. I guess one thing I should have said before, when we were looking at that E sub n for the hydrogen atom, minus 2.18 by 10 to the minus 18 over n squared in our last chapter, if I'm talking about any one electron creature like helium plus, which just has one electron, you multiply by z squared, where z is the atomic number, and square it and multiply that, and that will give you the helium plus energy. That's why it's 4 times, because helium's atomic number is 2, 2 squared is 4. Lithium 2 plus you would multiply by 9, right? But it only works for one electron atoms. Effects on other electrons, well then it's a different story. So that's how that works. Okay, so the phone got me off topic, but here I am back again. And what are we looking at? Oh, right, okay. So screening is what I talked about. The book goes into too much detail about it. I'm not going to talk about it much. Just say the screening of the nucleus is more effective Electrons in compact orbitals pack around the nucleus more tightly than do electrons in large diffuse orbitals. As a result, the effectiveness in screening the nuclear charge decreases as the orbital size increases. So if you have a really inner shell of electrons, that's going to be a better screener than a more diffuse larger orbital. But usually we don't need to go into that much detail about it. That's why I'm skipping through the screening a bit more. And let's get through the photoelectron spectroscopy, and let's get to the bulk of the matter here, which is using the orbital information that we know to get electron configurations, and from there we can return and look at properties such as electronegativity, electron affinity, ionization energy, and atomic radii. So the periodic table, here you're cutting things out. There's a Pauli, was a guy involved with it, all sorts of guys. To help with the periodic table, Dmitry Mendeleev, of course, the guy who's credited as the creator of it all. Some people would dispute that. Pauli mentioned the idea that an electron in an atom has a unique set of quantum numbers. No two electrons in an atom can have the same set of the quantum numbers N, L, M sub L, and M sub S. Okay? So each electron in an atom has a unique set of quantum numbers N, L, M sub L, and M sub S. And that means that there can only be 2 electrons maximum per orbital, because let's say I'm looking at helium, so one of them could be 1, 0, 0 plus a half, 1 electron, and another electron could be 1, 0, 0 minus a half. Okay, well then if we go to lithium, which has got 3 electrons, so helium's got 2 electrons, those would be the quantum numbers for each, for one electron and for the other. Lithium, well, I could have, well, be 3 electrons. Would I do 1, 0, 0? I can't. So I have to go to the next n value. I have to go up. So 2, 0, 0 plus a half or minus a half and onward. So that idea of the Pauli exclusion principle helps us understand the off-ball principle. Off-ball means to build up. And so when you're getting a configuration, arrangement of electrons for more than hydrogen, you use build-up. Oh, I see here that they've changed it and called it construction. Okay, so that's now the meaning, the agreed upon meaning for off-ball means construction. So you're constructing an arrangement of electrons in an atom or an ion. You start with the most stable subshell first and go up from there. So I can sneak it in there. First you have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 4f, 5d, oh boy, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 4f14, 5d10, 7p, whatever, then 8s. Okay, so the ground state is the most stable state. This is just a bit too much data. Here you go. Each electron in an atom occupies the most stable available orbitals. No 2 electrons can have identical quantum numbers. Orbital capacities are as follows. The S is 2 electrons, the P set, in other words, the P subshell 6 electrons, D subshell 10, F subshell 14. The higher the values of n, the less stable the orbital. For equal n, the higher the value of L, the less stable the orbital. Okay, so in terms of filling, I can also remind you of what I call the terrific trapezoid. Some of you may, I'm reminding some of you I haven't taught before, but the terrific trapezoid is a way to remember the filling. So I go from 1s up to 8s, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and then the p's, I got 2p, 3p, 4p, 5p, 6p, 7p, and then the d's, I got 3d, 4d, 5d, 6d's, and then the f's, I got 4f and 5f. So you see how it makes a trapezoid. And what you do is you fill up the 1s subshell first, and then you fill up the 2s, and then the 2p3s, 3p4s, 4p5s, 4d, 5p6s, 4f, 5d, 6p7s, 5f, 6d, 7p, 8s. So that's the order in which you fill up the subshells, and that is what I call the terrific trapezoid. And I don't know anyone else in the world who calls it that, but maybe there is somebody out there. Okay, here we have the electron configuration in terms of the blocks for electron configuration. So our main group elements are those where the last electron dumped in is in either the S block or the P block, and then the last electron dumped in, if it's in a D subshell, then it's a D block, and then inside, if it's an F subshell, it's called the intertransition metals, also known as the lanthanides and the actinides, and that's F blocks. And I think a few of you were in a TikTok video we did last year where we marched into the room chanting like monks, and we did the chants. But the way it works is, let's say we were looking at bromine, so you look for the natural breaks. So you go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And that is the electron configuration for bromine. There's different ways to do electron configuration, but that's one way. Or if I want to do lead, there it is, 82. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then you go to the F's, 4f14, 5d10, 6p2. So that is the chant way of doing the periodic table. And there's another way to show it, okay, in figure 510. And let's try some examples. Let's get the electron configuration for germanium. So let's get the full electron configuration, sometimes called SPDF notation, or sometimes just called the electron configuration. So germanium, so I meant to bring up a periodic table, but I forgot it, so I'll just go to the top of first page in the textbook. Germanium is 32 electrons. So 32 electrons. So I write germanium, then I write how many electrons there are. It's neutral germanium. And this is the ground state electron configuration of germanium. We can talk about excited states too, but for now let's talk about the ground states electron configuration of these many electron atoms. So for germanium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That gives us 4, 10, 12, 18, 20, 30, then 4p2. So that's 32 electrons accounted for. We know that the valence electrons are the ones which are in the highest n value subshells. So there's 2 in the 4s and the 2 in the 4p. So there's 4 valence electrons in germanium. And lo and behold, it's in group 4. And I'm going to say, no, it's in group 14. But remember, we can also call that group 4 in the older way, and I think better way, for valence electrons. So our group 4A. So that makes sense. You'll see some books will put the 3D10 before the 4s2. That's not wrong. I don't like doing like that. I like keeping it this way because that goes with the trapezoid. But once it's all said and done, if you want to group your ones, your n equals 1s, n equals 2s, n equals 3s, and n equals 4 together, that's okay. You're still saying there's 2 electrons in the 4p subshell. It's just not written at the end. But the way I do it is the way most people do it. Okay, let's try zirconium here. The full electron configuration for zirconium. And zirconium is going to be, help me out here, shout it so I can hear it, 40 electrons. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6. Quick way to get you started is, you know, zirconium is in group 5. So, sorry, it's in, not group 5, it's in period 5. So you will start the 5th period with s's, so you can go up to get to the 5th period. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Now zirconium is 40, so I think it's 5s2, 4d2. Does that up to 40? Let's see. 2, 4, 10, 12, 18, 20, 30, 36, 38, 40. So that is the electron configuration for zirconium. Okay. There's another notation, I might as well throw it in here, called the abbreviated notation. And the abbreviated notation is also called the rare gas notation. Some people call it the core valence notation, but rare gas notation is good. Rare gas, of course, is group 8. So what you do is you look for the nearest rare gas to zirconium, but not more than how many electrons there are on zirconium, and add up, build up from there. So the 4p6 takes me to the end of krypton. So I got krypton. So to get zirconium, you write krypton in square brackets, then 5s2, 4d2. Okay, so that would be the rare gas notation for zirconium. Now, in terms of valence electrons, some people don't deal with valence electrons for transition metals. They say, that's a bit controversial. But if you really have to, what you do is you take your highest value and the number of unshared electrons, sorry, just the number of electrons in the value 1 less. But this is only done for transition metals. So this would have technically 4 valence electrons in the transition metal concept, and that's why it's in group 4b. Okay. Yeah, so valence electrons are those of the highest principal quantum number plus those in partially filled d and f orbitals. Fine. Okay. Then a bit of history there. Electron configurations. Well, I already started electron configurations, and the book is going all sorts of glorious detail about it. Here's aluminum. Oh yeah, they do these little pictures for aluminum. That's one way of doing it. 13 electrons. So 1s2, 2s2, 2p6 is 12, 3s2, and 3p1. Okay, so that is aluminum. I can write what's called an orbital box diagram for aluminum. So aluminum, 13 electrons. So I'm going to have 1s, 2s, and the 2p, and then the 3s and 3p. So you write your subshells and you put these little mini boxes which represent the orbitals. So there's 13 electrons. So watch this. Let's change the picture here. Color. So I have one electron spin up, one spin down. So there's a spin paired electrons at the 1s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I got 3 more. 11, 12. And then I got the 13th electron, which I can put in any box in the 3p subshell. So we see that we have 3 valence electrons in aluminum. This is called an orbital box diagram. In the olden days, they'd write it with circles and have diagonals going through the circles. So this is a bit longer way, but it does show you a bit more information on how things are done. Let's sneak one in here for oxygen. Or actually, let's just do practice exercise 5.3. That'll work too. Determine the energy level diagram in shorthand notation for fluorine. Well, shorthand notation, let's just get the electron configuration for fluorine. 9 electrons in all ways that we know. How about that? So 1s2, 2s2, 2p5, that's one way. Or we can write it as helium, 2s2, 2p5. There's really not much of a savings in terms of an abbreviation like that. With the orbital box diagrams, we'll have 1s, 2s, and then we'll have 2p. Okay, so 1s2, 1, 2, 2, 2s2, 2, 4, and then 5, 6, 7, 8, 9. So we see how that works. And an interesting one, let's do oxygen with the orbital box diagrams, 8 electrons. So you got 1s, 2s, we got 2p, one, 2, 3, 4, 5, 6, 7, 8. So in these 2p subshells, the electrons are first distributed evenly with 1 electron in each, and typically you draw them spin up, and then you got the 4th one and you put it spin down. You could put it in any of them, but typically we put in the first one that we draw. So what I'm saying is you don't have like 2 electrons in one mini box or 1 orbital and 2 electrons in another mini box and nothing in the third. That's not allowed. You have to distribute the valence electrons so that there's 1 in each of these degenerate, that means same energy, p orbitals, before you start doubling them. And that is known as Hund's rule. H-U-N-D''S. Hund's rule is associated with that. Okay, some people ask they just want the valence configuration, so then you would just write 2s and the 2p, 2s2, 2p4. Electron configurations, why do we care about them? Because lots of reasons. They help us with predictions and explanations of periodic properties, help us with reactivities, help us with bonding. Okay? Shorthand electron configuration, that is the book says shorthand, they mean the rare gas notation. As I see here for indium, I have krypton and then the rest of it. Full configuration, well then you're going to put in all this stuff here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p1. The superscripts are how many electrons there are in each subshell. Some students get confused. They see 2p6, they say, no, you can only have 2. But remember, it's the 2p subshell. So there's 2 electrons in each of them, so it's a total of 6. And the 1s is the orbital designation, 2s is the orbital designation, etc. And this book likes to, instead of the boxes, use these little circles, and that's okay. That's another method of doing it. So that's allowed. Hund's rule, I talked about that. Sulfur atom, 1s2, 2s2, 2p6, 3s2, so that's 12. and then there's another 4 to make it 16. So if you just write it as 1s2, 2s2, 2p6, 3s2, 3p4, you're good. That's the complete configuration, or there's the abbreviated one. If you want to write it with the box diagram, you see here you got the 3s2, then you got 3p4. So you got 1, 2, 3, and then one going down. This book likes to do full arrowheads. I don't. I like doing smaller ones. Here we have for nitrogen, we got 7 electrons. So let's use the orbital box diagrams. You got 1s, 2s, and then 2p. So 1, 2, 3, 4, 5, 6, 7. So there are the 7 electrons. Valence set. Okay, so let's look at one of the valence electrons here. So the N will be 2, L would be 1, M sub L, you could choose 1, 0, minus 1, whichever one you want. I'm pointing it up, so it's plus 1/2. And then this one could be 2, 1, 0 plus 1/2, 2, 1, 1 plus 1/2, that's fine. One of these guys could be 2, 0, 0 minus 1/2. And this one spin up 2, 0, 0 plus 1/2. And again, remember the Pauli exclusion principle says that these are the only 2 possible electrons that can go into a 2s orbital, which makes up a 2s subshell, right? 2s subshell is made up of 1 s orbital, and so that's how that works. As a little aside, some of you might remember something I wrote last year. That shells are made up of subshells. Subshells are composed of orbitals, and electrons live in the orbitals. So shells, subshells, orbitals, electrons. Some orbitals are really close in energy to each other, and 2 examples are copper and chromium. So chromium you think might be 4s2, 3d4, but instead it's an exception, and it is actually the rest of the atom electron configuration is 4s1, 3d5. Okay, so not 4s2, 3d4, but 4s1, 3d5. And copper, you might expect, would be 4s2, 3d9, but it's not. It's 4s1, and they got 2, 4, 6, 8, 3d10. So 4s1, 3d5, 4s1, 3d10. Okay? So those are anomalies to what we have. And one reason this is because you have a bit more stability if you have a half-filled or completely filled set of degenerate orbitals in a subshell. So there are some exceptions and this special stability, and you need more quantum mechanics to really get into all of this stuff. Electron configuration of ions. For most, filling is the same concept, but when we get to cations of transition metals, it gets a bit trickier. So if I have something like Na+, well, there's 10 electrons, so that's okay. In fact, it's got the same electron configuration as neon, the same electron configuration as fluoride, all of them 10 electrons. And a word that's going to be important in this course is isoelectronic. So these atoms and ions, they have the same number of electrons. They're said to be isoelectronic. Okay? Now, for the transition metal cations, experiments show that transition metal cations, the d orbitals are always more stable than the s orbitals. So you kick out the s orbitals first. So Fe3+ contains 23 electrons. So let's write it in. Well, let's write iron itself. Iron is going to have 26 electrons. So iron is going to be argon. Let's about 8 more. Let argons be argons. Iron is in the 4th row. So argon 4s2 3d6. So that's 8. Is that right? 8? Yeah, 26. Iron has 26. Iron 3 plus, what you do is you're going to say, well, you might think, oh, well, I filled up the 3Ds first, so they're the first ones to go out. But that's not true. Once it's all filled up, they all have this discussion and say, okay, this is the way it is, but now kicking out electrons, oh, we got some electrons in the n equals 4 shell. Those go out first. The n-1d electrons are always more stable. So yes, use the trapezoid, but then you don't use it anymore, and you just say, okay, so Fe3 plus, you kick out the 2 electrons from the 4s and 1 from a d, so it becomes argon 3d5. So that's Fe3 plus. If I wanted Fe2 plus, that would be argon 3d6. Okay? Vanadium is argon 4s2 3d2, and Fe3 plus cations have different electron configurations, even though they each have 23 electrons. Okay, well that's fine. That's okay. Let's go to yeah, here. Okay, just show you exactly what I meant. Here's a vanadium. So you got 4s2 3d3 and Fe3 plus. You don't have any in the 4s, but you have 5 in the 3d. Okay. So they have different valence electron configurations, even when the species contain the same number of electrons. What's the ground state of chromium 3 plus? Well, chromium is 24 electrons, so chromium 3 plus is 21. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d 1, right? Let's see, 18. If I was just doing chromium by itself, it would be argon 4s1 3d5, right? Remember that was an exception. So 3d plus, I'm going to get rid of the 4s and 2 of the 3ds. So it's going to become argon 3d3. Okay? By the way, when you're looking at this, something we'll look at, you say that the chromium 3 plus cation has 3 unpaired electrons. All the other electrons are paired. But here in the valence part here, 3 unpaired electrons. There isn't anything spin down. Determine the ground state electron configuration compact form of ruthenium 3 plus. Where the heck's ruthenium? There it is. It's got 44. So it's krypton. Ruthenium itself would be krypton, then 5s2 4d6. Let's count that up. So that's 8, and krypton is 36, so 44. So that's good. But I want ruthenium 3 plus, so I get rid of the 5s2 and one of the 4d. So ruthenium 3 plus is going to be krypton 4d5. Okay. So count the total number of electrons, add electrons for ions, subtract for cations. This is guidelines for building atomic or ionic electron configuration. Fill orbitals to match the nearest noble gas of smaller atomic number. Add remaining electrons according to Hund's rule. For neutral atoms and ions, place electrons in ns before n-1d. For cations, plus electrons in n-1d before ns. And there's exceptions and corrections. And then I started to talk about this. If you have an atom or an ion where all the electrons are paired up, it's not attracted to a strong magnet, and it's termed diamagnetic, like helium 1s2, right? The electrons are paired up, so we say helium is diamagnetic. But iron is paramagnetic. In fact, It's actually ferromagnetic. It's got lots of unpaired electrons, right? Iron, we're going to have argon, and then we're going to have 4s2, 3d. Iron's 26, so 3d6, right? Because that's 8 and 18, so that is 26. So it's going to have 4s2, so that part's paired up. And then I'm just writing this here, 3d, 1, 2, 3, 4, 5, 6. So it's got 4 unpaired electrons. That's a lot. So iron is attracted to an external magnetic field. So as long as there's at least one unpaired electron, it's paramagnetic. Otherwise, it's diamagnetic. Okay, iron 3+, well, that would be paramagnetic. Iron 3+, yeah, that's paramagnetic as well. Okay, so you could check out things as we see in example 5.7, where you have F- Zn2+ and titanium. So you got 3 there. So you want to know which one, if any, are paramagnetic. So if there's an unpaired electron, then it's going to be paramagnetic. So fluoride's got 10 electrons. That's got a nice filled shell, so there's no partially filled orbitals, so it's diamagnetic. Zinc 2+, 30 electrons, and the cation is 28. Or the parent zinc atom is 30, the cation is 28. So it's argon 4s2, 3d10, but I get rid of the 4s2, so there are no partially filled orbitals. So it's also diamagnetic. But titanium, you see that there are 2 unpaired electrons in the 3D subshell, so it is paramagnetic. Okay, then there's some practice questions to do with that. Okay, we won't talk much about electron configurations of excited states, but we should at least look at what we mean by that. You have, let's say, sodium in its ground state, 1s2, 2s2, 2p6, 3s1. If you zap it with a bit of energy, you can excite any of the electrons up to a higher level. There's all these rules about which goes where, but you could, for example, take the 3s valence electron and kick it up to a 3p. So that is one thing you could do. Or you could take one of the electrons in the 2p subshell and kick it up to the 3s. But they're less stable than the ground state. Each atom or ion has only one state that is most stable, and that is the ground state. Excited states have practical applications. Street lamps, we talked about those. Dazzling colors of a fireworks display come from photons emitted by metals in excited states. The red light in highway flares come from excited strontium 2+ ions. So there are practical reasons to do this, and you can try the section exercises on your own. So that's good. We'll get into the periodicity of atomic properties in the next class. Have fun.